With line integrals, instead of integrating over an interval or a region, we integrate over a curve. Here's what I mean by an interval or a region. When we first learned how to integrate over a function f in the xy plane, we integrated over an interval, say from a to b. And our integral, of course, looked like an integral from a to b of f of x dx. When we started considering functions in 3-space, we considered how to integrate them over a region. Our function gave us a surface, s is equal to f of xy. The region was d, and our integral looked like a double integral over d of f of xy dA, and this d is the region we're talking about. So instead of integrating over an interval or a region, we integrate over a curve. We can still think of this function x and y, but the curve we're talking about exists in the xy plane. Let's try a curve in a different position there. And we can imagine that this curve exists within the shadow of the surface, and on the surface, let's try that again. On the surface, say, is basically the intersection of the cylinder that would go through that curve and the surface itself. The curve that we're talking about here is in the xy plane, and we're actually going to consider integrating over, say, part of the curve. And the meaning of the line integral will depend on context, but for now what we can say is in R2, if I'm integrating over an interval, what I can find is the area under the curve. In R3, if I'm integrating over a surface, then what I can find is the volume underneath the surface. For the line integral, one way to think about what we have is that if the function f is positive, then the line integral can give us the area of the one side of basically the sheet that exists between the curve and the surface. Now that can be one interpretation of a line integral on the plane, but we could also consider a function f of x, y, and z in space. Now for line integrals on the plane and in space, if we consider a parameterization of a curve C so that a point in R2 is parameterized x of t, y of t, then we can find the line integral of a function f of x of t, y of t over C by dividing C into subarcs that correspond to subintervals for the parameter t. Let's see this visually. Suppose we have a curve C, and the curve corresponds to an interval for t that goes from a to b. Now on the curve C, p sub I minus 1 and p sub I define a subarc. And that subarc can correspond to a subinterval t sub I minus 1 to t sub I. Now, as we've seen before, if we consider a representative element within the subarc, call it p sub I star, then say that corresponds to a t sub I star. And the idea here is that for these values of t, we map to points P on the curve C. And t sub I star maps to an element in the ith subinterval of C. Now the subarc from p sub I minus 1 to p sub I is denoted delta s sub I, and I'd like to point out this is a lowercase s. That will matter as we move through the chapter, not necessarily this section. Now for the line integral of C over the as t goes from a to b, in order to compute that, we form a sum. The sum as I goes from 1 to n of f of x sub I star y sub I star, that corresponds to p sub I star, times delta s sub I, and then take the limit as n goes to infinity. The result is what we call the line integral of f along c. That's the development. It's not how we're going to compute it. As you might expect, we're going to have an integral symbol here over c f of x y ds, which equals the limit of the sum that we just saw. Now, if ds looks familiar at all, it should. It's the length of the arc. And using the expression for arc length from a previous chapter, we get that the integral over c of f of x y ds is equal to the integral from a to b of the parameterization f of x of t, y of t, times the square root of dx dt squared plus dy dt squared dt. That ds that we saw before is that same arc length formula that we saw in a previous chapter. That is the two-dimensional case. For the three-dimensional case, we'd have the line integral over c of f of x, y, z ds is equal to the integral from a to b of f of x of t, y of t, z of t times the square root of dx dt squared plus dy dt squared plus dz dt squared dt. Again, that square root times dt is the 3D analog for the arc length. These can be represented as the integral from a to b of f of r of t times the magnitude of r prime of t dt. Recall that the magnitude of r prime of t was given in a previous section as ds dt. We called it speed then. If we treat this first derivative as a fraction, because first derivatives act like fractions, and multiply both sides by the differential dt, then we have that ds is equal to r prime times dt, which is exactly the expressions that we have underlined in pink. This is referred to as the line integral with respect to, which I'm going to abbreviate WRT, arc length. We can also consider line integrals of f along c with respect to x and with respect to y. And those look like the line integral over c of f of x, y dx, and the line integral over c of f of x, y dy. And what those look like, for dx, it would be the integral from a to b of f of x of t, y of t, times x prime of t dt. And that for dy is just about the same, except a y prime instead of x prime. Now this f of x of t, y of t, those describe the curve C. And if we consider the curve C as a vector function r of t, then it has components x and y. That's what's going on inside of the argument of the integrand here. Once we know what x and y are that describe the curve C, then we substitute those in place of x and y in the original integrand. We end up with something solely depending on t. You will see examples of this as we go. Now these can actually be added together, and the expressions are replaced. We have p of xy dx and q of xy dy. Both of these are line integral over c. And right now, just keep in your mind that p is going to go with dx, q is going to go with dy, and in what I would have thought was an abuse of notation, but I've gotten used to is a single integral over c of p of xy dx plus q of xy dy. So that's just an abbreviation for the sum of the line integral over c with respect to x and the line integral over c with respect to y. And the 3D analog would look like a line integral over c of p of xyz dx, q of xyz dy, r of xyz dz. Don't worry too much about what the meaning of these things are at the moment. You're going to see some examples of this, and before this section is over, we're going to see some connections here. Now, as I was saying above, we're going to end up with things in terms of t when we're, well, let's go back. When we're looking at things from the perspective of f of x of t, y of t, and then our x prime of t, y prime of t, and even further back here when we talk about ds, all of this stuff is in terms of t. Therefore, since our integrals are in terms of the parameter t, our first step is often to find a parameterization for c, or for c1, c2, and so on, say up to cn, in the case that c is composed of a finite number of curves, c sub I.